Hey there, and welcome to The Explainer. Today, we are going to dive into a really powerful technique used in chemistry labs all over the world, thin layer chromatography. You'll probably hear it called TLC for short, and it's a fantastic tool for separating all kinds of mixtures.
So, have you ever wondered about the black ink in a pen? Is it really just one single black substance, or is it secretly a mix of different colors? This is exactly the kind of question scientists ask all the time, and they have a really clever way to find the answer. Let's see how they do it.
Well, the whole science behind this is called chromatography, and the basic idea is pretty simple actually. You take a mixture, like our pen ink, and you pass it through a special kind of material. This material interacts with each part of the mixture a little bit differently, and that causes them to separate from each other.
You know, the easiest way to get your head around this is to think of it like a race, a great separation race. And in this race, there are two really important things. First, you have the racetrack, which we call the stationary phase. It doesn't move. And second, you have a pushing wind, which we call the mobile phase. This is the part that moves and pushes everything along the track.
So here's our game plan for today. First, we'll talk more about this race analogy. Then we'll introduce TLC and see what makes it special. After that, we'll go through the steps for running the experiment in a lab, learn how to calculate the results, and finally figure out how to make your separations even better.
All right, let's kick things off with Section 1, the Great Separation Race. We're going to see how this simple idea explains how chromatography really works. Okay, so the whole principle behind this race is actually super simple. Just imagine that all the different chemicals in your mixture are runners. Now, some of these runners are stickier than others. They like to grab onto the racetrack, and that really slows them down. But other runners are more slippery. They don't stick to the track, so the wind just pushes them forward really easily. And it's that difference in speed that separates them.
Okay, so now that we've got the basic idea of the race, let's zoom in on our main event for today, thin layer chromatography.
So why do chemists use TLC so much? What's it good for? Well, it's a really fast way to check if a sample you have is pure or if it's actually a mixture of different things. You can just count the spots to see how many compounds are in there. You can even use it to help identify a substance you don't know. It's often a quick first step before doing a bigger, more complicated separation. Now, in our TLC race, the racetrack is usually a plate that's coated with a substance called silica gel. And the most important thing to know about silica gel is that it is very, very polar. You can think of polar molecules as having a slightly positive and a slightly negative end, kind of like a tiny little magnet. So this polar racetrack loves to attract other polar molecules.
And that brings us to our sticky runner. If a compound in your mixture is also polar, it's going to be really attracted to that polar racetrack. It sticks to the plate, which means it moves very slowly and doesn't travel very far.
And then you have the complete opposite, the slippery runner. A nonpolar compound isn't attracted to the polar racetrack at all. It doesn't stick, so it gets pushed along very easily by our wind, the mobile phase. These compounds are the fast ones. They'll travel much farther up the plate.
All right, theory is great, but how do you actually do this in a lab? Let's walk through the steps of running a real TLC experiment.
It really comes down to 5 basic steps. First, you get your TLC plate ready. Second, you prepare your sample, usually by dissolving it in a small amount of liquid. Third, you carefully spot a tiny bit of your sample onto the plate. Fourth, you develop the plate by putting it in a jar with your solvent. And finally, fifth, you look at your plate and see the separated spots.
Okay, first big mistake alert. This is super important. When you draw your starting line on the plate, you must use a pencil. Why? Well, think about it. The ink inside a pen is a mixture itself. So if you use a pen, the TLC process will separate your pen ink right along with your sample, giving you a bunch of extra spots and completely messing up your results.
And here's another huge mistake you want to avoid. When you put the plate into the jar, the level of the solvent, the mobile phase, has to be lower than your starting line. If the solvent comes up over your spot, poof, your sample just washes away into the bottom of the jar, instead of racing up the plate like it's supposed to.
So the race is run, the plate is developed, now what? We need to analyze our results. And that means it's time for a very important but very simple calculation.
We do this by calculating something called the retardation factor, or just RF value. You can really just think of it as the final score for each of our runners in the race. It's a number that tells us how far a specific compound traveled compared to how far the solvent traveled in total.
And the math is super easy.
The RF is just the distance your spot moved up from the starting line divided by the total distance the solvent moved up from the starting line. It's a simple ratio, and it will always give you a number between 0 and 1. So here is the most important relationship to remember. The more sticky a compound is, which means the more polar it is, the less it's going to move, right? It gets held back by the plate. A shorter travel distance means a smaller RF value. On the other hand, a slippery, nonpolar compound travels really far, giving it a much larger RF value, something closer to 1.
But what happens if your race doesn't look right? What if all your spots are just clumped together at the top or stuck at the bottom? Let's figure out how to fix that and get a better separation.
Okay, first problem. What if all your runners just zoomed right to the finish line? All their RF values are close to 1. This means you're pushing wind, your mobile phase is just way too strong. To get a better separation, you need to make the wind weaker. You need to use a less polar solvent to slow everything down.
And then there's the opposite problem. What if your runners are all stuck at the starting line? Their RF values are all close to 0. Well, that means your wind is too weak. It isn't strong enough to get them moving. The solution? You need to make the wind stronger by using a more polar mobile phase to give everything a better push.
This quote really sums it all up perfectly. The whole magic of the separation isn't about how fast a compound is on its own. It's all about the differences in how well each compound sticks to the racetrack. That stickiness is what separates everyone out in the end.
So there you have it. You now know the rules of this amazing separation race, which makes me wonder, as you look at the world around you, from the colors in a flower petal to the dyes in your food, what mixtures would you want to investigate next?